Well, it's quicker, number one, and it's probably easier for you guys to tolerate if you have to look at it. We can zoom. God damn, this is cool. All right. Now, the whole point of what we're doing, if you remember the title, if you will, from Thursday, is called estimating a population proportion. And as Lindsay has correctly pointed out already, that guy has a name, little p. But we don't know little p, we know little p hat. Using the sample for Gesundheit proportion p hat. That's the idea of today. That's the idea of today, is figuring out an estimate for that based off of the snapshot you got of the population. All you get is a snapshot. Okay, so that's our big idea. Now, Will asked a very, very good question, because there is a part 1, 2, and 3 whenever you have to estimate anything statistically, anything. The first thing is you draw a simple random sample. Okay, we agreed what that was last time. Any sample has the same chance of being chosen. Was our sample simple random? Was it a perfect simple random sample? Was our sample of all pennies that are out there? What do you think? What does your gut tell you? Was it a perfect? Was it the best possible simple random sample of pennies we could have possibly asked for?
No.
No, not even close. Why?
Because you provided them.
Say, Rosie?
Because you provided them.
Exactly. I provided them to you. Somebody even commented on it. It was Cassie. The bag is ripped. It's got holes in it because I've been using the same damn pennies for 13 years. Right? They're old pennies. The new style penny didn't look that way anymore. They changed it back in 06 or 07 or 2012 or something. They changed the whole makeup of the coin. Not the most perfect. Is it random-ish enough? Yes, definitely. Definitely, because I'm hoping that if the Mint is releasing these coins, they're fairly consistent. And that snapshot of coins pre-2012 is all pretty consistent from one coin to the next. Believable? Fair-ish? Good? Yes. Now, we got our simple random sample. Then we go for the center of the sample, which we just figured out, which is p hat. And the third requirement is the margin of error. I want to end with that. There are a few other requirements, though. There are a few other requirements. There are a few other requirements for this kind of statistical exercise. Whenever you have to estimate a population proportion. You'll realize this as you go through this course with me. Every time you run a test or an interval or something like that, you have to satisfy a checklist. Did you do this? Is it like this? Is it like this? Is it like this? And if you can check off all those things, then yes, it's okay to run whatever test we're talking about. And this is a problem, or it can be a problem when you go into the world to do statistics, because you can do statistics on just about any numbers you want, but that doesn't mean it tells you anything. You can do a bunch of wrong math on a bunch of great data and get a completely wrong answer, and the test itself won't tell you squat. It'll just happily provide you with a number and go, here you go. And you go to your boss and you go, okay, you built that bridge 14 inches wide. It turns into Spinal Tap. You mean 14 feet? No, I mean 14 inches. And you won't know the difference because the result came out and it looks fine, and the test doesn't warn you. So here are the checklists we have to do for this particular assessment. We have to, first of all, we have to make sure we have a simple random sample. We're going to check that one off. Oops. We're going to put little check boxes next to it. We're going to go through these to make sure our penny experiment actually checks them off. We've got to make sure we have a simple random sample. We're going to give ourselves credit for that one, even though it's not perfect. You have to have a fixed number of trials. You have to have a fixed number of trials. Okay? The probability of success, and while we're at it, the probability of failure have to stay consistent. These are check boxes. We'll come back to these. I want to come back one by one. And there's one last one that is not at all obvious. I'm going to start by putting it in quotes. You have to have enough trials. What does enough mean? It's a good question. You have to satisfy these two inequalities at least. I want to spend a great deal of time today explaining that last bit to you, and then re-answer it even better. So, here's the checklist for running this kind of... You guys agree, we all had the calculators out last class, and we ran through this, boom, and an answer came out. But the question then is, should we have even done that? Should we have even done that? Well, let's just go with this and go through the checklist real quick together. Did we give ourselves simple random sample credit? We gave ourselves credit for that. It's good enough. It's good enough for argument's sake. It's good enough. You know what? Let's do this. Let's put pennies above this, because we'll do a couple more experiments to get two all right. Were there a fixed number of trials in our experiment? Were there a fixed number of trials? Yes, because I gave you all a penny and I said, go do what with it? Go spin it 10 times and see what happens. I did not say keep spinning it until you get half heads and half tails. I said go spin it. Go spin it 10 times and then write down what you got and come back. Boom. Good. When I say probability of success and probability of failure, does that ring a bell? Success and failure? Two things happening, either succeeding or failing. What does that sound like from 243? Yes, it's definitely the binomial range. It's all this is the binomial. Because either it lands heads up or tails up. We did have a discussion about the potential for it landing on its edge. And Kaylee, I think you said it stayed on its edge for a while and then eventually fell over. But that's a 1 in a million shot, according to my data. So we're going to let it go. We're going to let it go. And we're going to say that there are only two outcomes. And these meet the binomial criterion. We're assuming that the pennies aren't changing while we're spinning them in any way. So can we say that the probabilities are constant? I think so. It's a fair assumption to make. It's a fair assumption to make. Some of this stuff has to be assumed because you don't know it. Now here's the weird one. You have to have enough trials, and I want to get into this a lot today. When I say enough, mathematically, and I'll demonstrate why for you momentarily, you have to show that your sample size times whatever your perceived probability is has to be at least 5. And Q is the chance of failure. The chance of failure times your sample size has to also be at least 5. Now let's stop just for a moment and realize the problem with that statement. What does this assume that we know?
Probability.
Yes. The very probability that we are trying to figure out. So it's a bit of a cat chasing its tail or a dog chasing its tail here. We want to estimate a proportion, P. We want to make sure we have enough data to do it. So we check this and it says, okay, as long as you have enough data times P is bigger than 5, and time out. We don't even know what P is yet, right? So here's one way around that. Create a value for P. Create a value for P and keep trying sample sizes until you satisfy that inequality. There's a better way, but this is the base way. I want to work off of this. So what value for P did you guys think of automatically when we started this? When I said, what is the chance that we're going to get heads after spinning? You said 50%, 0.5. If P is 0.5, what is Q? Also 0.5. Good, so that's easy. If this is 0.5, what would N have to be
10.
to make this true? At least 10. Did we do at least 10 trials? My goodness, we did 260. So, assuming that P is 0.5, we did enough trials, didn't we? So we're good. So we're good. But suppose it's not 0.5. Suppose it's 0.4. Suppose P is 0.4. With me so far? With me so far? If P is 0.4, that means Q is 0.6. How large of a sample would you need if this was 0.4 to get that times 0.4 equals 5? It would be 5 divided by 0.4, which is 50 divided by 4, which is 12.5. Did I do that right in my head? Did you do that right in my head? Check me on that.
Sounds good.
12.5? I'm guessing it's 12.5 in my head.
Yeah.
12.5. So if P is 0.4, we'd have to have 12.5 here. How about if Q is 0.6, don't even bother checking that. Why? Because n would have to be smaller, wouldn't it? So, in other words, whatever the smallest of these two is, you can check that one to make it okay. So now you're like, oh, 12 and a half, we did 260, we did 20 times what we needed there. What if P is really, really bad, like 0.1? Suppose it's 0.1. Well, if that's 0.1, what would you need here?
A larger number.
You need a larger number. You then need what? 0.1, 50 versus, or 100, excuse me, 100. No, 50, I said the first time. 50. And if it's 0.01, you need 500. And if it's 0.001, you need 5,000, and so forth. And it starts going up and up and up and up. But the thing of the matter is, once you start splitting the pennies, you realize it's probably not 0.001 or 0.01 or 0.1 or anything like that. It's pretty close to the 0.5, isn't it? So, how do you feel about this requirement right here? Okay, maybe a little okay? I'm going to put a question mark next to it for now. I will come back and re-answer that question better. Come back and re-answer that question better. You know what? Not the hell with that. Let's do it right now. Let's answer it right now. Right now. Swing this back around.